This is the last week of instruction, so we're doing review 3 for your exam. And your exam should be available on Canvas. It is technically due this Thursday. You can work on it till the end of the semester. So try to finish it by the 13th. If you want more time on that test or any other assignment that you have not done before, just let me know and I can unlock it and you can finish it by the 21st. Okay. So that's the very, very last day of class. After that date, I'm going to start working on final grades and we won't be able to do any more classwork. Cool. So your test is only on graph theory. So that's what we're doing today, review for graph theory. So graphs are vertices that are connected by edges. The vertices are the dots and the edges are the lines. So, dots. Or I'm just going to put are equal to vertices. And one dot is a vertex. And the lines are called edges. It doesn't have to be a straight line. Graphs are vertices that are connected to each other by edges. And it has to go from one vertex to the other vertex, touching both of those vertices. Like the edge has to touch both sides. E-A-C-H. Okay, well, here you go. With one dot, that could be a graph all by itself. Just something over here labeled X. That's a graph. It's got 0 edges and one vertex, the vertex X. And let's do like A connected to B, so their vertices are A and B. And your edge needs to start at one vertex, go to the other vertex, and touch it. Like there's this connection all the way from A over to B. So that's my graph. I've got two vertices, A and B. And my edge is AB. Or BA, either way. Just, you don't have to repeat the edge, but they are the same thing. So AB is equal to BA. But if there's only one edge, list it one time. And that's because we did do graphs that had multiple edges. So let's do this graph. Right, we called that one a loop. When you go from a vertex back to itself using an edge. Here you've got multiple edges. So 3 edges between those two vertices are called multiple edges. And we're going to label this R, S, T. Cool. So listing the vertices is pretty easy. So RST. And we're going to have the edge RS, RS, RS listed all 3 times. And ST, and then TT. Let's go on to talking about degree. So the degree of a vertex is the number of edges that touch or that connect to the vertex. Okay, degree. Number of edges. Or maybe to like a vertex. Cool. This one, we're going to do the degree on the side, starting with R. So this would be degree, DEG, of R. And you've got 1, 2, 3 connections. S has 1, 2, 3, 4 connections. So you're going to have degree of S equal to 4. And degree of T. So your loop adds 2 to the degree. You've got 1 connection, 2 connections, 3 connections. 1, 2, 3. Okay. I'm going to stay here with degree, but we're going to have a new graph like this. Let's do this shape. It's kind of a stop sign. And we'll put a vertex in the middle of that edge right there. So now I've got 2 edges. And let's put some multiple edges right in here. Okay, and start with P. P, Q, R, S, T. And we're going to get the degree of every vertex. Oh, and so using this notation, degree of P is 3. We've got 3 connections. 3, Q. 1, 2, 3, 4. Degree of R is 3. Let's work around to S, which has degree 2. Degree of T has 1, 2, 3, 4 edges connected to it. That's degree 4. And V has degree 3. I mean, W has degree 3. We're going to have to work on V next. Okay, let's go with this little diagonal here and then go around. So starting with 1 connection, 2, 3, 4, 5, 6, 7. Cool. And I think we'll go on to talking about walk path circuit, which will later bring up degree again. So a walk. Is a sequence of vertices. Each vertex is connected to the next by an edge. Let's go ahead and draw a new graph. I was hoping to use this one, but there's like a million in the book, so get on with this. Connected to the next vertex by an edge. Okay, I think I want to do this kind of post off of a triangle shape like this. We're going to do some multiple edges. Over to here. Let's put an even extra little edge and vertex at the end. Okay, and A, B, C, D, E, F. So the walk goes from vertex to vertex using an edge. Something that is not a walk is something like AF is not a walk. A to F. Let's go B, D, C, B, A. That's a walk. B over to C, over to D. We're gonna have D go back to B, B over to A. And that one is a walk. Let's go from let's just go between A and B. We go A, B, A, B, A, B, stop. So I would go A to B, and then back to A, and back to B, and back to A, and back to B. So like went over this edge a bunch of times, but that's okay. It's a walk. Again, we can always draw a new graph. So the next one we want to talk about is a path. In a second now. Cool. A path is a walk, and you do not reuse an edge. Any edges. So we have this graph over here from the book. There's a loop around vertex E. And straight over to B. We kind of come over a little bit at an angle to get to C. Then we're going to go up to A. A is also connected to B. And then go from A across here and call this D. Then D goes to E, or D has a connection to E. Okay, so we've got A, B, C, A, D, E. So A over to B, over to C, goes to A, goes to D, ends at E. Let's check it. So starting at A, make your way to B, and over to C, and you can use either of the edges. C goes to A. A goes down to D. then end at E. So I have gone from vertex to vertex using an edge, and I used every edge one time. So this is a path. Okay, next one we have let's go B. Let's just start at D. It goes D, E, E, B, A. So we're going to start at D, and let's go with a swirly shape T. Then E to E using the loop. Go from E to B. B to A, and stop. So use every edge one time, and it's a path. Let's talk about a circuit, and then we're going to stay with this graph and find a circuit. So a circuit needs to be a walk where you go from vertex to vertex using an edge. It needs to be a path where you use every edge only one time. Or if you use an edge, it's only one time. And you end up where you started, or you start where you end. So if you see something, like I'm just going to make something up really fast, like D, B, C, D. Just because you start at D and you end at D, you should check that it's also a path and that it's also a walk. So you should be going from vertex to vertex using an edge, and use your edges one time and end where you start. But I think D to B is not even a walk. So it's not a walk. And it definitely can't be a path or a circuit. Something like, let's just go ABC. That would be a circuit. Oh, ABCA. That would be a circuit. So starting at A, going to B, it's just like super shape. A to B, B to C. Let's just go this way, around here. There's this other edge to get from B to C, and C up to A. Started A, I ended A, I use these edges one time. And the book's got A, D, E, B, A. this up for a second. Okay, so we're going from A over to D. And go up to, A to D to E to B to A. That's what we're trying. Over to E, just upwards. That's going to send us to B and to A. Cool. We went and did this route, which is the path. Oh, actually, it's not only a path, it's a circuit. We started where we ended, and it was also a path. Okay, one more. EE is technically a circuit. You go to E and just travel around the loop back to E. You start where you end, you use your edge once, and yeah, it's all good. Okay, walk path circuit. Now we need to do Euler path, Euler circuit, two results, and that's all the stuff we learned about graph theory. That's everything you'll need to know for your exam. So an Euler path is a path that uses all of the edges. An Euler circuit is a circuit that uses every edge. So we kind of just want to probably use the results instead of actually finding Euler paths or Euler circuits, which you can. You can do like scratch work to find the actual path or circuit that uses all of the edges in your graph. But there's a shortcut. So if you want to know if you have an Euler path, check the degrees of your vertices. Okay. If your graph has exactly two odd vertices, or only two odd vertices, then you will have an Euler path somewhere in your graph. If there are no odd vertices, then an Euler circuit exists. You don't have to actually find it, but you know that there is one somewhere in the graph. Okay, if there's not too odd or there's no, wait, if no odd means if it's all even, more than 2 odd is the other option, which means you don't have an Euler path or circuit, so neither of them exists. Cool. So we're going to practice, but this should be the end of the material that we've covered for graph theory. This result, and the third one. And just being able to apply these ideas to something kind of wordy, like, we'll just jump right into that one. So the word problem is about being able to travel through a neighborhood using each street one time and ending where you start. Okay, so a mail carrier wants to visit each street once. Okay, so the map is drawn as a graph. And it looks like, let's see this one. It looks like a kind of square shape. And then we are going to do a extension here and a connection there. Then go ahead and make another square shape down this way. Like visit this other part of the neighborhood. And let's add an extra little like street on the end. Okay. We do scratch work, where we check the degree of all of the vertices. We don't need labels, we're just going to put the degree in parentheses right next to the vertex. So this is a degree 2. This is 2. This is degree 1, 2, 3, 4. So far I'm doing good because I've got even degrees. If I find 2 odds, then I've got to maybe say that I've got an Euler path. If I find more than 2 odds, I don't have an Euler path or Euler circuit. If there's no odds, I have an Euler circuit. And so far I haven't said anything about needing to start where we end, so I'm looking for at least an Euler path. An Euler circuit would be nicer because the person can make their trip and then end where they start. But if they just have a goal of making the trip and they can be picked up later from wherever they end, then an Euler path is just fine. Okay, so here we go. Degree 3. Yikes. So not going to have an Euler circuit because it's not all even. We just found an odd. Okay, let's see if we can find an Euler path. So keep on going. There's another odd. It's at degree 1. Just did that one. This is degree 2. And then a degree 3. So I could go ahead and stop right now, I think. I've got more than 2 odds. This one, this one, this one means that I don't have an Euler circuit or an Euler path. So it's not possible for them to make this trip. Let's see, how do they say it? It is possible to take a stroll through the... No, not that one. In a single pass. Okay, it's not possible for the mail carrier to make the trip in a single pass. Or on your test, you can be more specific about like an Euler path or Euler circuit does not exist. So it's just like saying the same thing. Okay, so let's just practice on plain old graphs. Just going to find a graph from the end of the section, and we're going to just jump straight into looking for Euler circuit or Euler path. Actually, this one's cool. It goes like, let's go here. Okay, so starting the new problem where you go from one vertex with multiple edges to the next vertex, multiple edges here, swoop, vertex, swoop, oops, over here, and then connect those two. Okay, so does the graph have an Euler path or Euler circuit? So we check the degree of the vertices. If there's 2 odd, it's got an Euler path. If there's 0 odd, it's got an Euler circuit. Or if neither of those happens, then it's got neither of those things. So degree 3. So we already know that it's not going to have an Euler circuit. Degree 3 again. So it could have an Euler path as long as we don't have any more odd vertices. But that one right there is also degree 3. And just for fun, we're going to check the last one, which is degree 1, 2, 3, 4, 5. So this one has all odds. But even just more than 2 odds means you don't have an Euler path. So if you put neither, that would be fine, but I would probably want to spell it all out and say that the graph does not have an Euler path or an Euler circuit. Okay. And now, like a few more examples, and then we'll come back next time and do a lot more examples, and that's it. So we're going to try taking this graph, finding if it has an Euler path or Euler circuit. So there's a star like this. We are going to go over and over and across, over, over. Okay. Might even just stop there. Let's give that a go. Looking for an Euler path or Euler circuit. So look for degrees. Just go ahead and label everything at first. Degree 2 all the way over here. And 2. And 1, 2, 3, 4. Oof. So this is, oh wait, hang on. There's 1, 2, 3, 4. We're still cool. Once, twice, 3 times, 4 times is even. That's even. It's degree 2, and degree 2, and degree 2, degree 2. So if I've got all evens, then I've got an Euler circuit. I also have an Euler path, but if you have an Euler circuit, just go for the stronger definition. You can just write that and get full credit on your test. So use the best definition, but if you also put that it has an Euler path, that's fine. It's just extra. I think we should do one more, and then that's that. Let's make this shape. It's like a shape and a shape and a shape, and then we'll check it out after we're done. Starting with a big square. And then inside is a diamond where we've added some vertices halfway between like each of those other edges we just made. Inside the diamond is another square. And that's the graph. So that's the graph. So check all of your degrees, and as soon as you find more than one odd, you know it's not an Euler circuit. More than two odds, it's not an Euler path. And then you could stop at that point if you want. So degree 2. Degree 2. Another 2. Once, twice, 3 times, 4 times. And a 2. 1, 2, 3, 4. 1, 2, 3, 4. So good so far. We could have an Euler circuit slash path, but we keep going and look at that vertex and those other ones with degree 1, 2, 3, 4. They should all have degree 4. So we've got all evens again, which means we have an Euler path. There's an Euler path and an Euler circuit, but Euler circuit is stronger. So we're going to say it has an Euler circuit. All right, so if you have any extra questions that you'd like to work on next class, we can just spend time doing practice on Thursday. So that's it for today. Thank you for coming to class.